Welcome to this video on the difference quotient. First, we're going to take an algebra perspective on what a difference quotient is. If you're given a certain function and you're asked to find a difference quotient, what you're actually being asked to compute is this quantity right here. And while that may seem strange, there's a reasons for this that we'll see later. But this is the definition of a difference quotient: to algebraically calculate the quantity you see there on your screen. So to get out of the abstract, let's look at a particular function for which you might be asked to do this. Suppose you were asked to do this for x squared minus 4x plus 5, for example. What I'd like to do here is take a quick look at the process here, and then we'll reverse it and slow down and look in more detail at the algebra later. Let me give you a brief overview before we get into the nitty-gritty algebra. So to compute the difference quotient, we should first compute f of x plus h and negative f of x for the particular function given. Now I've done that here algebraically, and don't try to follow every little symbol, but once you've worked those out, you can then simplify the expression using algebra until you get a result. Now, if you think your algebra skills are very strong, then in a minute I'm going to have you hit pause and see if you can track all this yourself in terms of the actual algebraic detail. If not, I'm going to guide you through it. If you're up to the challenge, hit pause now and see if you can sort of figure out all the details on your own. This thing here at the end is called the difference quotient, but now let's take a more detailed look at the exact same problem, going through all the algebraic steps. So to compute the difference quotient, again, we have to compute f of x plus h. You may see it in red in front of you. And we have to compute negative f of x before we can complete the rest of the calculation. So let's go through these one at a time. First, let's just focus on f of x plus h. What does that mean? That means to take the particular function they gave you and replace the x's with x plus h's and do all of the associated algebra. So what I've done here is expand the x plus h to the second power. You may see it in blue, and I'd like to point out or remind you that exponents don't distribute, so I actually had to use FOIL to do the blue section here. Continuing on the algebra, by distributing the negative 4 to the x plus h, I've now simplified this expression as much as I can. You'll notice that even though we have 6 terms here, none of them are alike, and therefore there's no combinability. So I have now computed f of x plus h. Now let's turn our attention to the negative f of x. I'd like to remind you that negative f of x means negative 1 times f of x. We simply don't write the times sign or the 1 in most cases. And that, with that perspective in mind, negative 1 times f of x means negative 1 times the function you were given, which, if you distribute the negative 1, works out to this. And I now have the negative 1 times f of x worked out in my algebraic expression. And now that I've worked the two functions out, I can use my basic algebra skills to finish. One thing you'll notice here is that there's a lot of cancellation. The x squared and the minus x squared combines to 0 or cancels. The negative 4x plus 4x combines to 0 or cancels, as does the positive 5 and negative 5. So after all the cancellation of terms, we get down to this. By the way, in general, when computing a difference quotient, you will almost always encounter a lot of cancellation of terms, and if you don't, you've probably made some mistake at some point. But I'm not done calculating this because I now have to divide the numerator by h. One way to do this would be to divide h into each term. Another perspective would be to factor an h out of the numerator, because then I can cancel it with the h in the denominator using the fact that h divided by h is 1 and the associative property of multiplication. Anyways, there is your final simplification here, and that's what we call the difference quotient for this particular function. Of course, any function you could be given has a different difference quotient than any other in most cases, but this is the difference quotient that's associated with this particular function. Of course, this raises an interesting question. Why do we care? What does this difference quotient mean? What does it have to do with anything? Well, for the rest of this video, we're going to look at a graphical perspective using the same example to get a sense for what this means. So, with that in mind, let's proceed. So let's take a look at the same problem graphically. You'll recall just a few moments ago we were given this function. We computed the quantity called the difference quotient, which again is defined by this formula. And we did a ton of messy algebra that led us to 2x plus h minus 4 as our difference quotient. Now, a brief warning here, I'm about to take you into a mental journey here that summarizes a decade of research in calculus that happened sometime in the 1600s. So I'm not showing you the kind of math problem that you would necessarily do in a mathematics course. What I am showing you is some ideas that were developed a long time ago that have led to some very important discoveries. So let's take a little journey into math history. Here is the graph of f of x, or the graph of x squared minus 4x plus 5, as it turns out. So what does the difference quotient mean? What does 2x plus h minus 4 represent? This is what they figured centuries ago. Imagine a point, just any old point on this graph, with a particular x value. The mathematicians asked themselves the question, what would happen if we would go over a random amount to the right of that, say h spaces? Well, we would then be h spaces to the right of x, or at x plus h, which would correspond to a new point on that graph. And mathematicians ask the question, what if we drew a line through those 2 points? That line, by the way, is called a secant line. And the question that was asked was, could we find the slope of this secant line? Well, it turns out that the difference quotient, the thing that we just calculated with all that messy algebra, does represent the slope of the secant line. Now, to convince you that this does in fact represent the slope of the secant line, follow me on this mental path. The slope of a line can be computed by the change in y over the change in x, also known as rise over run. Well, to compute that, I would have to know the rise between these 2 points. The run, of course, is h, but how do we compute the rise? Well, the rise is going to be the vertical distance between the 2 y values of those 2 points, the lower of which is f of x, because it has an x coordinate of x, generically speaking, and the higher one will have a y coordinate of f of x plus h, because the x coordinate is x plus h. And so the rise, or the distance between those 2 points, would be the top one minus the bottom one, or f of x plus h minus f of x. Now, if you got a little lost in that, don't feel bad, most people do. The concept there is that the difference quotient isn't some random algebraic formula somebody made up. It's a formula that was derived to represent the slope of the secant line. And if you're not totally sure why, or got somehow misled in the details there, don't stress that. but it's nice to know where this formula for difference quotient came from. At the end of the day, if your professor asks you to find the difference quotient and you don't know where the formula came from, you can still use it. No problem. But why do we care about the slope of the secant line? Well, here's some other thoughts that mathematicians had centuries ago. Mathematicians asked the question, what would happen if this distance h, the horizontal distance between the 2 points of the secant line, what would happen if it shrunk? And what if it got even smaller? And what if h continued to shrink to the point where h was gone and literally zero? Well, then this line here, you may see it in blue now, this line would no longer be a secant line. It would be what's called a tangent line, a line that has the same slope as the curve that it hits. And so the difference quotient, which again represented the slope of the secant line, could be transformed by putting a zero where h is to represent the notion of h shrinking down to nothing, as we just saw. And then that quantity should represent the slope of the tangent line. Algebraically, that simplifies to 2x minus 4. So what does that mean in this picture? Well, when I drew this picture, I picked an x value of about 2.4. And even though we talked about this generically with x being any quantity, the actual point that I selected on this curve just so happened to have an x value of 2.4. So if we were to plug that x value into the slope of the tangent line equation that we created by letting h shrink to 0, and we were to work that out, which I did, by the way, it works out to about 0.8, then we would have found the slope of the tangent line to the curve. So hopefully now you can see the importance of the difference quotient. The difference quotient gives us the slope of secant lines as a function of h. But if we imagine h shrinking to 0, then that formula becomes the formula for the slope of the tangent line. And not only can I then find the slope of the tangent line when x is 2.4, as it was in this particular picture, but you can see how I could find the slope of the tangent line for any value of x, anywhere on this curve I wanted. And that turns out to be a very useful tool in mathematics and science. If you're feeling a bit confused here, that's normal. It's partly because the math is difficult, but it's also partly because, in some sense, I've told this story a little bit out of order. Let me give you the same information about the graphical importance of the difference quotient in a more logical fashion. Suppose we have a particular function, and on that function we have a point and a tangent line. And suppose we want to know the slope of that tangent line, because that ultimately is the goal of the difference quotient. Now, in order to find the slope of a line, we need to know 2 points on that line. But here's a problem. We only know 1 point on this line. So in order to sort of artificially create a second point, we introduce the notion of the secant line, which is not the tangent line, but we imagine that the secant line is something that we can compute the slope of. So we go over an arbitrary distance, which we call h, horizontally between the 2 points on the curve or the 2 points on the secant line, and we compute the slope of that secant line using the difference quotient. After some very ugly algebra, we got a result. Now that result is the difference quotient. And if that's all the question is asking you, there's no reason to consider the tangent line. The reason why difference quotients are important is because they give us slopes of secants. Slopes of secants are important because they can lead us to the slope of a tangent. So we imagine that the slope of this tangent line would be the end process of imagining that h, this arbitrary distance, were shrinking and shrinking and shrinking and getting closer to 0. And if we did that, our difference quotient, or secant slope, reduces to 2x minus 4 in this case. And once we have the formula for the slope of the tangent line at any point x, we can then use it to find the slope of the tangent line at a specific value of x by just plugging that value in, thereby finding the slope of a particular tangent line. That is the ultimate goal of computing the difference quotient, because that it leads then ultimately to the slope of the tangent line. And that completes this video on the difference quotient.